Hi, my name is David, and I'm going to be talking today about binary search. Binary search is a pretty simple approach to finding something in an array. And we're going to illustrate this with an example array right here. So let's say we have an array with 7 elements. And this array is going to be in sorted order. This is actually pretty important. So we have 1, 3, 5, 6, 7, 9, 10. Is that? Okay, that's 7 elements. Let's say that we're tasked with finding a target number. And let's say that target is the number 9. So what is one intuitive way to solve this problem? Well, the most obvious solution would be to look from the very start of the array and check every element if it is equal to our target. And if it's not, we can move on to the next element. If by the end of the array, we don't ever see our target element, then we can conclude that the target isn't in the array. So we perform that. We look at the first element, which is 1. 1 is not equal to 9. Cross it out. 3 not equal to 9. 5 not equal to 9. Blah, blah, blah. And the 9 is equal to 9. So now we can conclude that the target is found in the array. But what if there's a better way to solve this problem? Let's look at the exact same array again. Uh, so note one thing is that the fact remains that all of this is in sorted order. So one easy way to implement a binary search approach towards this problem is to look at the first element and then the last element, and then store some kind of pointer to each of these elements. So between these elements, we're going to look at the very middle element. The one in the middle would be the number 6. We ask ourselves the question just like we did last time, except with one caveat. Instead of asking just whether 6 is equal to target or not, if it is not equal, we look at whether or not 6 is smaller or larger than the target number. So since right here 6 is less than 9, we can conclude that 6 is not possible to be, 6 is not the candidate, and all of the numbers to the left of 6 are also not the candidate because it's in sorted order. So all of the numbers before 6 have to be less than 6, and 6 is less than the target, so no way that the numbers to the left of 6 are equal to the target. Therefore, we can instead move this pointer over to here. Now we can only need to search this little space. The middle element between the pointers now are going to be is the number 9. And there we go. We found the number 9. So this approach makes things a lot easier for us. And one intuitive way to think about binary search might be to just might be thinking about it in terms of looking things up in a dictionary. If we're looking for the word volleyball, we don't need to go through aardvark and then all the stuff that starts with A's, and I don't know what else is at the start of the dictionary. But you can instead, quickly scan and move over to, around the middle or towards the end where V is. So there's a easier way to solve this problem in real life intuitively than there is with the very easy approach that we did at first, which is just to count every single element from the very start, which is kind of pointless. But okay, let's see how we can use binary search to help solve some problems that we were assigned. So the first problem is going to be LeetCode number 35. Um, I think it is called search insert position, and it is a really good example of how you can use binary search. So it is a pretty simple problem in terms of how it's laid out. So you have an array of like 1, 3, 5, 6. We'll say it's like that. And then you have two conditions. So the first thing is that if the target number is in the array, then we return the index of the target. The second condition is if the target is not in array, target not in array, not in array, we return index of where it would be, of where we'd insert it. So if we look at the example of 1, 3, 5, and 6, let's say that the target is equal to 3. So we're going to label these indices 0, 1, 2, 3. And if the target is the number 3, then we would return 1 because 3 is found. But let's say that the target is actually, let's say that the target is, say the target is 4. So if the target is 4, then what we will return is the value 2. Because 0 and 1 have 1 and 3. 4 is larger than 3, but less than 5. So you would move the 4 into this position, and then kick 5 and 6 down. So in terms of using binary search for this problem, it is a pretty similar approach to what we had before, except the last thing to keep in mind is just to make sure that you return the right pointer at the end. So normally, in this case right here, if we did not have our target found in the array, let's say that we have the number, um, not 9, but let's say that this was 11 and then this one was 13. So we would first look at 11, and then we'll see that 11 is larger than our target value. So we can cross out 11 and everything to the right of it. Then we'd move the pointer over to here, 7 and 7. So the middle point between these pointers is just 7 because they're at the exact same location. But 7 is larger than, 7 is less than the target. So what happens is that we move the right pointer, no, sorry, we move the left pointer over to the right one. And at this point, we can cross out 7. But one thing that happened is that we noticed that the pointers actually switched. So this one was the right pointer, and then this one was the left pointer. But now they swapped locations. That means that we've looked through all of the elements in the array. Well, in this case right here, so where the pointer swaps to at the very end is a helpful hint for where you might want to insert an element that you did not find. So that's just a hint for that problem. We're not going to go through all of it, but just a brief overview. The next problem I'm going to look at is 162, which is a find peak element. And this is an interesting problem because one thing you've noticed from all the binary searches that we've had so far is that the entire array is sorted. So we have 1 through 5, 6, 7, 9, 10, this one with 11 and 13, 1, 3, 5, 6. All of these ones require the array itself to have all of its elements in sorted position. But in this problem, the elements aren't necessarily in sorted position, which is interesting. So there's a couple of conditions right here. So basically the definition of a peak element is, let's say we have an array 1, 2, 3, 1. A peak element is one element where the neighbors to the left and the right are both smaller than this element. So right here, there's only one peak element in this array, which would be 3. And 3 is a peak element because to the left of it, 2 is smaller, and to the right, 1 is smaller. So you can also have multiple peak elements in an array. If you have 1, 2, 1, and then you have 3, 4, 5, 6, 3, you have a peak right here because 2 is greater than the 2 ones next to it. And then you have a peak at 6 because 6 is greater than the 5 and the 3. So there's two important things to recognize here. The first problem condition is that nums of I is not equal to nums of I plus 1. So you just need to keep that in mind. It'll help out. The last thing is that at the very end, nums of -1 is equal to negative infinity, which is also equal to nums of len nums. So what that means is that over here, there's a precipitous drop instead. We'll say that this is some infinitely low number right here. So let's say that instead we had the number 8 right here. 8 would also be a peak element because 8 is greater than the 3, and 8 is greater than this infinitely infinitely small number at the very end of the array that doesn't exist, but we just say that if it's at the very end, it is automatically bigger than the element to the left if it's on the very left end, or if it's on the very right end, it's automatically greater than the element to the very right. So right here, immediately you might think, hey, how are we going to use binary search? The numbers aren't sorted over here. But one helpful way to be able to think about this problem is maybe to draw a little graph for yourself. So for 1, 2, 3, 1, we say that this one is at 1, this is at 2, 3, and then this is at 1 or something. So we see that there's actually like a real peak right here, right? So for this one, for the second example, 1, 2, 1, 3, 4, 5, 6, 1, 2, 1. So this is 3 again, and then 8 is up here. So we have 3 peaks once again. 1 peak here, 1 peak here, and then wait. Oh wait, sure, I didn't draw that line. 1 to 2, 1 to 2, and then 1 peak here. So one helpful way to think about this problem is that even though the entire array might not be increasing or in increasing order, there are parts of the graph over here that are going to be consistently increasing. And then, once they stop being consistently increasing, that might tell you a little something about where the peaks are. So that's just going to be a brief overview on the basics of binary search and going over how you might want to use this concept in order to help yourself in some lead code problems. Yeah, thanks for watching.